Welcome back to the podcast, everyone. Mark here, and have I got something special for you today. We're diving into something that sounds like science fiction, but it's very much real, and, dare I say, mind-bending. Probabilistic computing.
And I'm Jenny, ready to have my mind bent, and hopefully not broken. Probabilistic computing, Mark? It sounds like we're talking about computers that, guess? Or just shrug their shoulders and say, maybe?
Haha, close, but in the best possible way. Imagine a world where computers don't just crunch numbers with certainty, like a light switch that's either on or off, 0 or 1. Instead, they embrace uncertainty, probability, and even a bit of controlled chaos.
Okay, so not just maybe, but, probably?
Exactly. And the reason this is so exciting, Jenny, is because it opens up doors to solving problems that traditional computers struggle with. Problems that are too complex, too interconnected, too messy for binary logic to handle efficiently. Think of things like optimization problems or highly complex simulations.
So we're talking about moving beyond the classic on-off binary bits. We've heard a lot about quantum computers with their qubits, the superposition, entanglement, all that jazz. How does probabilistic computing fit into this computational landscape?
That's a good question, and it really highlights the unique space probabilistic computing occupies. So, classical computers, right? They use bits stable, deterministic zeros or ones. Quantum computers use qubits, which can be both 0 and 1 at the same time through superposition, and they need super cold temperatures, near absolute zero. We're talking super fancy, super sensitive tech.
And they're still in the very early stages of practical application, especially for broad commercial use, partly due to those extreme environmental requirements and their error correction challenges, right?
You got it. That's where probabilistic computers, or p-computing, really shine. They use something called a p-bit. These p-bits aren't like classical bits, fixed at 0 or 1. And they're not like qubits either, in superposition. Instead, p-bits, they're constantly fluctuating between 0 and 1, randomly. But here's the kicker. They do this at room temperature. No cryo chambers needed.
Wait, so the randomness is a feature?
The randomness is the feature, not a bug. Unlike qubits, which need to be exquisitely isolated to maintain their quantum state, p-bits leverage thermal fluctuations. They're built using components like magnetic tunnel junctions, which are already used in memory chips, making them much more compatible with existing manufacturing processes. It's a distinct physical principle at play.
Okay, so they're not trying to be quantum, they're just doing their own thing, using classical physics in a clever way. That's interesting. But how does this translate into actual computation, if things are just randomly flipping?
This is the captivating part. Imagine you have a bunch of these p-bits, all fluctuating. You connect them up in a network, and you design these connections based on the problem you want to solve. Over time, as the p-bits randomly flip, they collectively, statistically, settle into states that represent the solutions to your problem. It's especially good for combinatorial optimization problems, like finding the best route for a delivery truck with 1,000 stops, or designing the most efficient circuit board. Problems where there are just too many times possibilities for a traditional computer to check them all.
So instead of trying every single path, it's feeling its way to the most probable good path?
That's a good way to put it. It's like a simulated annealing process, but built directly into the hardware. And the impact on energy efficiency? Oh wow, this is where it gets really compelling. Prototypes have shown a 10-fold reduction in energy consumption and a 100-fold reduction in the physical area, the silicon footprint, compared to traditional CPUs running the same optimization tasks.
100-fold reduction in physical space? That's like fitting a supercomputer into a shoebox. And 10 times less power, too. So this isn't just a theoretical concept. They've actually built these things?
They have. And some of the claims are, well, quite significant. We're hearing projections from some researchers of potential energy efficiency improvements of up to 100 million times better than NVIDIA GPUs for certain tasks. Now that's a projection, and it needs more validation. But even if it's a fraction of that, it's still, well, a major step forward.
100 million times? Mark, that sounds like something from a movie. Like we're talking about going from a gas-guzzling SUV to a car that runs on a single raindrop. Is this just expectation? Or could our data centers derive a similar benefit with this tech?
It's a large number, for sure. and we should always approach such claims with a healthy dose of careful examination until there's more independent, large-scale verification. But the underlying physics makes it plausible that the gains could be substantial. If even a fraction of that pans out, yes, it could change data centers, not just for energy efficiency, but for heat management too. Think about the cooling costs reduced.
So, P-bits operating at room temperature, using less energy, and tackling problems that stump classical computers. It almost seems too good to be true. What industries are we talking about here that would see the biggest benefits?
Definitely AI, especially in areas like machine learning optimization, training complex neural networks, and sampling from probability distributions. Then there's financial modeling, simulating markets, risk assessment, logistics, as I mentioned, optimizing supply chains, drug discovery, materials, science, any field with complex, multivariable optimization problems that currently take ages to simulate or are computationally too demanding.
Okay, so instead of a quantum computer trying to solve everything, which is difficult and expensive, a probabilistic computer could step in for a specific class of problems and do it efficiently at room temperature. It's pragmatic computing.
Pragmatic computing, I like that. And it gets even more interesting when you think about future architectures. We're not necessarily talking about probabilistic computers replacing classical ones entirely. Imagine hybrid systems, CPUs and GPUs, handling the general-purpose tasks, and then, for specific optimization or sampling problems, offloading those to P-bit coprocessors embedded right alongside them.
Oh, like a specialized turbocharger for certain types of computational problems? That sounds quite reasonable. Is that the biggest hurdle right now? Integrating these small, promising prototypes into larger, existing systems?
That is certainly one of the main challenges. Current lab models operate with thousands of P-bits, getting to millions, or even billions, and interconnecting them efficiently for complex megascale applications? That's still an unproven leap. And then there's the software side. We're so used to deterministic sequential programming, rewiring software and algorithms for this inherent randomness, and getting useful, reliable results out of it is a significant intellectual and engineering hurdle.
So what's harder? Building the hardware for millions of P-bits, or building the software to even use them effectively, given their probabilistic nature?
Honestly, probably both at the same time. It's a chicken and egg scenario. You need the hardware to test and refine the software, and the software to show the hardware's potential. But it's also about figuring out how to frame traditional problems in a way that probabilistic systems can understand and solve.
This brings up some interesting questions, though. If the results are probabilistic, if they're relying on randomness, what about ethics? If a probabilistic medical AI gives slightly different diagnoses each time, even with identical inputs, how do we regulate that? What about accountability?
That is a critical thought, Jenny. You hit on a key point: explainability and accountability. In a world increasingly reliant on AI, transparency is paramount. If a system's output can vary by design, it raises immense challenges for auditing, debugging, and legal responsibility. We need ethical frameworks and regulatory guidelines developed hand in hand with the technology before these systems are broadly deployed in sensitive areas like healthcare or autonomous vehicles.
Absolutely. It's not just about the technical feasibility, but the societal implications of inherently non-deterministic decision-making. Mark, you also mentioned something called G-bits in our notes. Is that like the next evolution of this, too?
Oh wow, Jenny, it gets even more compelling. So, P-bits are binary, right? 0 or 1. Researchers are already looking at G-bits, or Gaussian bits. These would be capable of representing continuous variables, not just discrete ones. So instead of fluctuating between just 0 and 1, they could fluctuate across a whole range of values, like a bell curve.
Continuous variables? So not just yes or no or on or off, but a little, a lot, somewhere in between? Where would that impact first? AI, or maybe something like material science?
That's right. That opens up possibilities for analog signal processing, more realistic neural networks, and extensive simulations like molecular dynamics or even climate modeling. Imagine simulating fluid dynamics or chemical reactions directly in hardware with continuous variables. It could be transformative for material science, drug discovery, or even real-time physics in gaming. It pushes the boundaries of what computing means.
From deterministic bits, to quantum qubits, to probabilistic p-bits, and now potentially continuous g-bits. This field is moving at a rapid pace, and it's exciting to think about the problems these machines might solve. But it sounds like we also have some serious thinking to do as a society about how we integrate something so inherently uncertain.
Certainly. The beauty is in the uncertainty, but so is the challenge. We've certainly got a lot more to explore here, and I'm sure we'll be revisiting probabilistic computing as it continues to evolve. For now, thank you for joining us on this interesting journey into the future of computation.
And thank you, Mark, for making the complex so understandable, even the parts that fluctuate. We'll catch you all next time. Don't forget to like, subscribe, and leave us a review.